Okay, so this is where we are with the planning. So as I explained, we proceeded very well with the validation.
For the first time in 2017, and are now recording collisions at an energy of 13 tera-electron-volt for the rest of the year. I was lucky enough to be here yesterday following this magic moment as it happened from the meeting at 8:30 in the morning in the room right up here, when the go for collisions with stable beams was given by the LHC machine coordinator, Stefano Redaelli. While we watched the clip of the moment as it happened, please prepare your questions, because I'll soon be joined here around this table by physicists from the 4 experiments and experts of the LHC accelerator. But let's take a look at the clip first.
Okay, so this is where we are with the planning. So as I explained, we proceeded very well with the validation overnight prior to the collisions. And if all the tests that have been done are successfully validated, we will be in the position this morning to declare the stable beams. So we will hopefully inject between 10 and 11. And if all goes well, we will be probably in the position to establish collisions in all experiments by noon or so today.
Good morning from CERN's Control Center. Today, May 23rd, 2017, a very important milestone is about to be reached in the LHC experimental calendar. I'm here in the LHC Operations Center with Rende Sterenberg, head of CERN Accelerators Operations. And today, Rende, your colleagues are going for the first time to achieve what in LHC jargon is called stable beam for physics for the first time in 2017. Why is it so important?
Well, this marks the start of the physics of 2017, and it's so important because now in the last few weeks we did commissioning with beam, and now we reach this crucial point in time where in fact we're gonna really go into collisions, and the experiments will take data out of these collisions. So that's for the very first time in 2017 again, and it marks the start of
the
this year's physics run.
So basically the detectors will switch on fully with all their components and start taking data for the rest of the year.
Yes. So we will have, today we will collide with a few bunches, and then in the coming days we will start colliding with more and more bunches. So this is what we call the intensity ramp up. And we want to go up to about 2,500 bunches.
With the 13 TeV energy, of course.
13 TeV, yes.
Okay, from the panels behind us, I guess we're not ready yet?
No, not yet. So we just had an access in one of the experiments. This is now finished, and now the injectors are preparing in order to get the beam ready for injection into the LHC.
So our next step is injection, and we'll come back to you when it happens.
We had to go with shorter bunch trains.
Yeah.
Normally we can go up to 280. So that you see all the peaks, the spikes, the green spikes.
Yes, yes, I see.
And that's the individual beam position monitors all around the LHC.
Yeah. 4 times. Okay, I'll give you a call. All right. See if you can help me.
He doesn't trust it?
Yeah. No, he cannot continue like this.
So the second stage has started. We are well advanced with the process of getting to the stable beams status. So where are we now?
So presently we're ramping. I just look at the display. So we're at 4 TeV. We have to go
per
to
beam.
6. Yeah, per beam. So we have to go to 6.5 TeV per beam, which gives the 13 TeV center of mass, and still ramping. So for the moment things go well.
So far so good.
So far so good. And we hope that the 3 bunches will make it to the top energy, and then we will do the squeeze and put the beams in collision.
Okay, so we are patiently waiting for these next stages to happen.
Yes.
Until stable beams.
Indeed. Yes, CMS.
No, stay here. And we are one step closer to stable beams because we reached the nominal energy of the LHC in its present configuration.
Yes,
that is
indeed.
the flat top, so-called.
Yes, so we're presently on the flat top, and just now the mode has changed from flat top to squeeze.
That's
So
great. So
this is-
an
this
extra
is-
step right
Exactly.
now.
This is the very next moment. So this is when we start reducing the size of the beams in the experiments
Yes.
before going into collisions.
The
so
thinner
that
the better, right?
Yes. So the more dense you have the beam, the more collisions you will have. And this is the
Okay.
idea of the squeeze. So you change the quadrupole magnets around the experiments in order to make the beam size as small as possible, and therefore we'll have more collisions.
And what's next?
So the next step will be to finish this squeeze. This will take about 10 minutes
Okay.
for all the power converters and the magnetic fields to reach the correct values. And then the next step will be to put the beams in collisions and then do the adjust. And this means that we will adjust the beams in order to maximize the number of collisions. So we steer the beams really head on so that the number of collisions will be maximum
Yes.
for
So
the
you
experiments.
adjust means they're still kept in parallel,
Yeah.
running parallel
Well,
inside
not at
the
that
LHC.
moment, but
And then you,
collapse, and then we
collapse.
adjust. Yes,
which means they will be colliding
exactly.
in the center of the 4 detectors around the 27-kilometer ring of the machine.
Exactly.
Okay, so that's happening very soon. I've seen another change
yeah,
of
that-
color in the.
Yes,
what's
but
happening?
this is the display of all the power converters, and
Yes.
and every time these power converters will change the current, we see the color changes on the display, and we see if all these power converters follow
I've
or
seen
not.
them going from green to violet. It's now yellow.
Yellow, yeah. So these are the different states, and the idea is that once we reach a stable state of the power converters, they become green again
Okay,
And,
so that's the sign for us to.
to end the squeeze.
Another step made towards stable beams. We are in adjust mode, right, Rende?
Yes. Right now we are in adjust mode, and this will take a bit of time, and then the beams will collide. So it's a matter of waiting. As you perhaps can see already, some
Everybody's
people,
waiting.
Additional people are gathering here in the control room.
And I'm sure in the
To-
4 experiments control room, they're all waiting
I think
for
so.
this
They're very
moment.
excited as well to see the first collisions in stable beams again.
So adjusting, let's explain again, what does it mean exactly, adjusting the beam
so-
before collisions?
So what we need after having done the squeeze, we need to put the beams head on. So we have to get the beams colliding, and then here the operations team, they will also optimize these collisions. So this means that
Perfect.
they steer the beam in such a way that you get the most collisions out of this beam.
So they get the best possible beam for the 4 experiments.
The highest number of collisions, yes.
Okay,
So there, I think
we are moments.
we're going
waiting
to,
for this
to
moment.
collapse the beam.
Which is the screens you're
Yes.
looking at most?
I looked at the power converter display because this announces the change of the power converters, and then we will look on the display. You see the display with the 3+3 over there,
Yes.
and then next to it is the display where we see the luminosity monitors of the experiments.
Okay.
So.
Okay. It's just
so
a matter of waiting right now.
It's now a
It
matter
could
of
be any
waiting,
time.
Yes. So if you look on the display now, you see that the collisions are there in CMS.
Yes. But the
And
experiments are
also-
not on again.
No. This is not yet the collisions for the
So
stable beams.
this is
These are
collisions mode of the machine.
This is
right?
in adjust. Now we have collisions in adjust mode. So now the
Voila.
people are adjusting these collisions, and then afterwards we're going to declare stable beam.
And then the experiments will switch on.
And then, only then, the experiments will start taking the data.
Okay.
They are switched on, but they're in
Not
standby.
completely. They're in
Exactly.
standby.
Yeah.
Exactly. Okay.
Exactly.
So it's a matter of seconds, minutes.
Well, this
Moments.
depends on the adjust time we need. So this is the operator that will declare it afterwards.
Okay.
So,
The
right.
sequence is launched.
The sequence is launched, so now they're going to push the button. Marcus?
Marcus,
go ahead.
is really a button? Is
yeah,
it really?
he's well, it's on the screen, but he pushes
It's
the
a button on the screen
and
to
then
make
he-
the beam collapse.
Well, the beams are already colliding,
Okay.
but now they adjusted it, and now they will tell
Give the
the experiments that they can start data taking.
Okay.
And now, stable beams.
Stable beams exactly at 4:31 p.m.
Yes.
on the 23rd of May 2017. The physics season has started at the LHC for 2017.
Very good.
Thank you.
Nice.
Hey guys!
Hey. Bravo!
And welcome back to the CERN Control Center. You've just seen the major milestone just accomplished yesterday, 24 hours ago, here from this room. First beams for physics started yesterday, the 2017 physics season, 2017. So we are here around this table with experts, physicists from the 4 experiment and from the LHC machine, to whom you can ask your question. Post your questions in the space right below this video box, and we will answer very soon. But first, let me introduce the guests around this table, starting with the LHC machine, Jamie Boyd. Jamie, hi. He's the LHC coordinator. Your role is sort of an ambassador between the LHC collider and the experiments. Tell us why.
Exactly.
Why do we need that? Why do we need you?
So my main role is basically to take requests from the different experiments and then try to come up with a configuration of the machine, running scenarios for the machine for the year that will satisfy what the experiments want, which sort of starts off before the run and is relatively, we come up with a plan, but then of course as the run progresses, what often happens is, we have issues which we have to change the plan at the last minute, and this requires sort of following very closely how the accelerator is working and also how the different experiments are working.
And you have to be very diplomatic, I guess, because there are 4 experiments, each with their requirements.
Exactly. We have to try and come up with the best solution to come up with the best physics to get out of the LHC, basically. So try and take into account the requests from all of the different experiments.
And talking about best physics, yesterday, of course, you were here. You were going through these fantastic milestones. You achieved first stable beams of the season.
Yeah.
Tell us, what's the difference between yesterday and the other seasons that we started in the previous years? What changes this year?
Yeah, this is a good question. So in order to try and get more data to the experiments, which is really the main goal of the LHC, we've tried to optimize the configuration of the machine. We try and squeeze the beams in a slightly different way than was done last year, which can give us more data. And we've also tried to remove some of the limitations that were in the machine last year that occurred during the year in the accelerator to try and be able to give more data to the experiments. This is really the name of the game from the accelerator side.
And we are constantly optimizing this fantastic machine.
Exactly.
Thank you for now. Stay here because I'm sure there will be questions coming from our live audience. We now go through all the experiments, starting from Atlas. Atlas is the largest of the LHC detectors. It's based in point 1. You can see on the map here. It's the experiment, the only one on Swiss territory, 100 meters below ground, Switzerland. So Alexander Ho is our Atlas physicist today. Yesterday, of course, you must have been in the control room as well, and it must have been, once again, an emotion to go through this first collisions day.
Yeah, certainly it was a great event to see stable beam collisions again in 2017. And we had lots of work was going into the detector because we had to prepare for new conditions. LHC did a great job of providing more collisions, as Jamie was saying, and this requires us, of course, to adapt our experiment so it can handle these more collisions. So there was quite a lot of work. New pieces of equipment were installed. A lot of things had to be followed up with these stable beams. So we had 5 different things going on at the same time, commissioning new pieces of equipment. And I must say it was really very, very exciting to see the first event on the display.
And we just seen them. I hope we can see them again. The first events, they were recorded exactly yesterday.
Exactly,
Here they are.
You see it so beautifully. You can see all detector components give you a signal in the spectacular event. You see a little muon there escaping to the upper left on the lower left screen there. So all the components worked beautifully together, and we could reconstruct this event, so it was really very, very exciting. And then, of course, after the first event, it subdued a little bit, so we were collecting more and more data, did all our tests, went through our program, which we planned ahead of what we would do with this first fill. And, yeah.
That's great. So now you have a better machine, you have more data. What's the plan for 2017 for Atlas?
So for Atlas, of course, the aim is to collect as efficiently as possible the collisions delivered by the LHC. So last year we had something in the high 90s, and of course we want to keep that performance, even though we will have more collisions this year. So we want to keep it on that level. And then with this data set, of course, we will roughly double what we had before at 13 TeV. So apparently we look for new signals in physics, new features, which is not described by the standard model. This is one program, a large chunk of the program of Atlas. And then, of course, on the other end, you have also precision measurements of known processes. And then you look for tiny deviations of what the theory really tells you it should happen, and then this could also be a sign of new physics. So this is the other branch of ATLAS, and there's also many more physics channels to be looked at.
So you're very busy. You will be very busy. And I'm sure there will be a lot of questions coming up for you. Let's now cross the LHC ring from point 1. No, they have a microphone here. From point 1 to point 5, interaction point 5, right above the circle up there, under French territory, sits another big detector, CMS. And we have here for CMS, Anne Dabrowski. Welcome, Anne. Tell us, how was the start of physics at CMS yesterday?
Incredibly exciting. During the year-end technical stop, so over Christmas and January and February, we installed our new inner tracker detector.
We did a Facebook Live of that as well. You can view it again. It was a fantastic operation, a heart transplant. It was dubbed by journalists.
Exactly.
Yes, it was a major operation.
Exactly. Yeah, this was the culmination of 5 years of detector construction work. And so our first stable beams yesterday gave us an opportunity to switch on this detector and see its first signatures with collisions.
So the heart is beating again
the
in
heart
CMS.
Is beating. Yeah.
Fabulous.
So the program was dedicated to timing in the detector, all the different layers. We have 120 million pixels.
And you recorded first events already.
Absolutely.
You brought events. There they are. Look at that.
There you can see, and that's in the CMS event display. You can see many overlapping events, and also signatures in our calorimeters. There you see the red muons bending in our magnetic field, and absolutely.
And this was just
day.
15 minutes after the switch on.
No, we
this is an incredible machine. So I've asked Atlas. I have to ask you the same question. What's the program for CMS this year?
Also exploiting the maximum potential of CMS, so we have to keep up with the increased number of particles that the LHC is going to give us per interaction. So this is creeping up every year, and now we have to reconstruct 40 to 50, 60 overlapping events. And so for CMS, we have to exploit our new pixel detector, image, 3D image, the location of all the individual vertices. And then, like Atlas, we're trying to look for new physics, and we're trying to understand in detail the difference between the theory predictions and the measurements in our detector to try and explore very small deviations, which could be hints of new physics.
Fantastic. And also Anne Dabrowski from CMS is staying around this table, is ready to take your questions. I encourage you to post them under the Facebook Live video. So now time to tour around the ring again. We continue going around and go to interaction point number 2. You can see it on the left bottom part of the screen. There's Alice. The Alice detector stands on French territory in Saint-Genis. And we have here for Alice Despina. I cannot pronounce your family name. I'm sorry. Can you say that? Okay, Despina is from Greece, but is one of the physicists of the Alice collaboration. So Alice specializes in quark gluon plasma studies. A stage of the universe when, very early universe, primordial universe, when the quark and gluons were deconfined, as you say. And usually you do that when the LHC runs lead-ion collisions, not proton-proton collisions.
Exactly.
And we learned from Jamie, he told me, this year, no lead-ion collisions. You will have proton-proton collisions. So tell us about Alice. What can Alice do with proton-proton collisions?
Well, Alice, of course, doesn't sit around when there are no lead collisions. We record data also with proton-proton collisions, and we use them in two ways. One way is as a reference for the lead-lead collisions, to do a comparison, and there observing differences in the two systems, we deduce that this exotic strand of matter, the quark gluon plasma, is formed in the case of heavy ion collisions. But also we do proton physics in itself with the possibilities that our detector offers us. And actually, lately, we published a paper which appeared in Nature last month, which is exactly the observation of something very interesting in proton-proton collisions. And this is that the observation that strangeness enhancement, which was one of the first signatures of this quark-gluon plasma, first seen 30 years ago, and which was associated only with lead collisions. We saw this phenomenon also in proton collisions at 70 eV. This is data from the first run of LHC. But in the particular case, when the multiplicity, which means the number of particles, the total number of charged particles produced in the collision is very high. So this is certainly something intriguing, which makes us have an extra interest in the proton-proton system. So we hope to study more with the new data that come this year. And in addition, we have requested for this year, at the end of the run, to have a dedicated run at lower energy, so that we can compare with data from lead-lead, which correspond to the same energy center of mass.
I see. So for sure you make the most of this proton run just started right now and for the rest of the year. Thank you, Despina. You stay with us. There will be a question for Alice, I'm sure. Let's now go to the last but not least, of course, interaction point around the LHC ring, LHC 0.8, which is very close to the Geneva airport, but still in France, in French territory, where the LHCb experiment is situated. We have here for LHCb Barbara Storaci.
Hi.
Welcome, Barbara. So, Barbara, also for LHCb, I guess yesterday was lots of excitement around the first collisions.
Yes, it's always a great emotion. I can tell you, since I'm a bit young, but I had the lucky fortune to be there every single times for all the collision, the restarts, also the very first one. And along the years, I thought that the emotion will go down, but in fact, no. Every time it's just a great emotion. It's just you are there waiting, and finally you see your detector alive again, your collision coming, and you know that you are ready for a new start of discovery, so of data that can really bring you.
We have one of your first events here. Can you comment on it?
Yes, so again, you can see that also in our case, a few minutes after the first collision, we produced this nice event display. You can notice that we are slightly different from the other experiment, in particular Atlas and CMS, that they have this cylindrical, or as I like to call it, onion shape. We are more like books in the shells. Yes. And you can see these lines are the trajectory of our particles, and one of the most important things is to try to reconstruct this trajectory and understand which particle produced them. And you can see really that all our detectors are alive and give a nice signature. So we are ready to start analyzing data and try to discover something.
What are your challenges?
Yeah, so these years are very exciting for us. So more data will come, and this will be very important, as my colleagues from the other experiment already said, because we saw in the previous year some potential discrepancy with the standard model, that we don't have enough statistics yet, so we didn't collect enough data to know if they are real sign of new physics or just, normal fluctuations. So now these extra data will be essential to see if they are still there, and we are at the start of a new era. So really, these are the years where you want to be here. I have a little feeling
that your preference is for discrepancy confirmation.
Absolutely.
So now it's time for questions. There are already coming quite a lot of questions. I have the first one for Atlas from Paul Johnson. Thank you, Paul, for this question. What energy is theoretically required to find evidence of superpartners, and at what point do you give up on supersymmetry? Alexander, big chunk for you.
That is a big chunk for me, exactly. So let's see. So the theory you're alluding to is probably SUSY, and of course the theory allows a wide range of masses for superpartners. Now, and the experiment, Atlas experiment at the LHC, is very well within that range that is theoretically allowed. So maybe the most prominent is the top superpartner, which should be one of the lower lying fruits, which he could detect if SUSY exists. And with the data set we have collected so far, the limit is about at a TeV or so, where we can say up to a TeV a stop does not exist, but maybe above. Now, you might argue we have 13 TeV at the LHC, so it's only one TeV. The reason is that not at every collision, not all that energy can be transferred into a mass of a new object. So there's a certain statistical process. So we hope with this more data we get now that we can either extend our knowledge to say it must be heavier than X, or, which is certainly the more exciting variant, is we discover it. So that
would be really exciting. There's now a question for CMS from Daranesh Sonu. Dark matter still remains a mystery. Does CERN think they can understand completely what dark matter is? You need a microphone. Yeah. Yes.
Well, I mean, certainly one of our searches is for dark matter, and how we look for it is we look in our event displays for missing energy. And if we can't explain that missing energy with, for example, a standard model particle like a neutrino, then we have to scratch our heads and try and understand what it is. It could be dark matter, or another thing is we look for processes that, So the question, can CERN contribute to the search for?
Search.
Yeah, I would say absolutely. It's one of our top priorities, and the collider experiments are well suited to looking for this missing energy. And of course, we also keep our heads onto the rest of the international community. Dark matter is also searched for in other underground experiments.
In
astrophysics, neutrino experiments, and so on.
Right. So you're all working together, and any hint from each of you is a step forward for all.
Exactly.
That's amazing. Okay, there's a question from Frederick Joseph Whittaker. Is live data from any of the detectors ever made available to the public or citizen scientists? Anyone wants to take this question? I know there is a program of participating in the data analysis from BOINC. I don't know, maybe you want to take that?
Yeah, I'm not sure. Maybe then we can have some help. So not totally sure about exactly what are the politics about that. But yes, I'm aware of this BOINC, or how it's called exactly, program in which you use the CPU from people around the world.
From this computer.
Exactly,
yes.
to contribute in the CPU needed for analyze the data. Then there is also some, I think there are some activities for students, for example, that you give some old data and you simplify. This is an kind of outreach, but not only activities to get the high school students to have a feeling and start to learn, and also maybe they become a physicist. Then there's also some program, I don't know if somebody here has more knowledge than me about the open data.
Yes.
So that's also quite an interesting thing. So it's a discussion that is, at least from what I know, ongoing in the community.
That's great. I have a question for you, Despina. Maybe it's also a question for Jamie. I don't know. You decide, why are there no lead collision this year at the LHC?
I don't really know, but I imagine that there was a big request from the other experiments to collect more proton statistics, and therefore the LED program was postponed for 2018.
Who decided that?
Yeah, I mean, I guess I'm partly responsible for this. The thing is, of course, we have different requests from the different experiments, and this year the physics data started a bit later than normal because CMS did this big intervention in their detector and replaced the pixel detector, which was a big intervention. And this means there's less days for physics data. So it was decided amongst the very big bosses at CERN that for this reason, this year we would just concentrate on proton-proton collisions. And next year we have the last month, so in 2018 we have the last month scheduled for lead-lead collisions, which will be for Alice, but also for the other experiments.
Great. Just a relaxing question for everyone. What is your fundamental particle? Let's start with you, Despina. What is your preferred fundamental particle? From YouTube, Tyler Codell.
My personal preferred particle?
Yes.
The electron.
The electron. You're a free electron. And you, Anna?
I have to agree. I'm an electron too, yeah.
That's great. Jamie?
Well, I'll go for the Higgs boson. Since I was around working on the Atlas experiment at the time when this was discovered, and I was sort of involved in this, so this was a very exciting time.
Oh, this is unforgettable, of course.
It's the easy one to go for, I'm afraid.
Alexander?
Yeah, I'm afraid I'm boring also. I was around when the Higgs particle was discovered, and then it catch my heart. So
yeah, this is a once-in-a-lifetime event in the life of a physicist, so... Barbara.
So here it's difficult. I'm puzzled between two answers. The big quark, because from LHCb, what can I choose, right?
Of course.
I should choose the big quark, right?
It's also beauty, so
yeah, exactly.
Yes, it fits you.
And then something that is more tricky here, maybe the neutrino. Why not?
Yes, a mysterious particle. And keep the microphone there. I have another question for you, Barbara, from Shivani. Yes, Shivani Mishra. What is the main problem the LHC is looking to solve this year? No, then it's not for you. It's for you. What's the main problem you have to solve? Well, you already solved it. You started the machine.
Does this question mean a physics problem that the experiment's trying to do, or the problems, technical problems on the machine side? So maybe I can comment on one of these. So the way that we give more data to the experiments is by colliding more and more bunches in the LHC, and the LHC is designed to collide something like 2,750 bunches. And last year, due to a limitation in the injector complex, so in the accelerators that feed the LHC, we were limited to 2,200 bunches, and this of course means less data to the experiment. So during the shutdown, as well as a big intervention in CMS to update their detector, the component in the injector chain that was causing this limitation was replaced, and this was very successful. And this year we hope to go to 2,550 bunches in the machine. So this will be a big step forward and allow us to give more data, more collisions to the different experiments.
Okay, so that's one of the challenges, of course. We have a question for a volunteer. I don't know who wants to take it, from Liam Samuel Mudge. Could the LHC be used to detect tachyons? Tachyons are hypothetical particles. I don't know if they are foreseen in the standard model. You have to tell me. Alexander, I see you have the answer ready.
Yeah, tachyons I heard first when I did a PhD thesis. There was Daisy in Hamburg and the Hera, so they're looking for this for a long, long time. But I have to admit I'm not a tachyon expert, so I wouldn't really know what the limits are and what the reach is. But so I don't know, maybe the others have a clearer view.
Yeah.
Tachyons are particles that go faster than the speed of light, is my understanding. And I think this isn't something that we're really looking for in the LHC experiments, because we're so confident from the standard model of particle physics, from the theory, that these don't exist. But of course this doesn't mean that people shouldn't start looking for them. And there was recently, a few years back at CERN, there was this big excitement because a neutrino experiment which shoots neutrinos from CERN to Gran Sasso in Italy, which is hundreds of miles away, came up with a signal that these neutrinos were moving faster than the speed of light.
So they could have been tachyons.
So this is something that could have seen tachyons. But on the other hand, in the end, after a very careful review of the analysis, it was found that this was a mistake in the analysis, and it wasn't really a signal for this thing, which would be very unexpected and would really rip the theory that we rely on apart. So this would be something very...
So it's not a precise objective. Then the next question is, what are the particles we are looking for now at the LHC? Let's start from CMS. What are the particles you're looking for now?
Well, as Alexander alluded to, the full family of potential SUSY particles are still up for the grabs. And then we're going to try and study the Higgs particle in much more detail, and understand if there is only one Higgs particle or if there are other Higgses,
which are
excited Higgses,
which are compatible with the theory.
Which are compatible with the theory, right? So we really are on the lookout for those. So that's and then of course our colleague from dark matter question and so on. So they
what would be a dark matter particle called if you found one?
Well, that's a
neutralino.
Could be a neutralino. Yeah, that would be a dark matter candidate from the SUSY model. And then there are other dark matter models as well that are not related to SUSY, and then these particles would get a different name. Yeah.
Another question.
Certainly we're on the lookout for neutralinos. Certainly, yeah.
Alice, what are your particles? Your preferred candidates you're looking for?
Well, as you know, we're not exactly looking for discovering new particles, but we are studying this more complex state of matter that is created from the heavy ion collisions. But then I wanted to add something else. I was last week at the LHCP conference, and there was a discussion, and it was mentioned that we can't hope for the discovery of new particles all the time. Somehow what we are trying to understand is the loss of nature. So with every new little thing that we find, we enhance our knowledge and our understanding of these laws. So that's not only particles.
Talking about particles, the next question, Frank Legris. Have you ever discovered something that you did not expect to find? Well, nothing is expected until you find it, by definition. And I know that even when you were very close to announcing the discovery of the Higgs boson, it was not clear whether it was that or something else, right?
Yeah, so I mean, the theory sort of predicted it. The lab, which was the accelerator complex before the LHC, the experiments, the data, all hinted towards that mass region.
Yeah.
And also the decay channels and so on. So we found it, but I wouldn't say it wasn't expected. So there were a good fraction of physicists who expected it, that it would be found. Well, we found many things which we didn't expect, which then in the end turned out not to be real. So these are like statistical fluctuations where the whole community is terribly excited about. And of course this can happen because it's a probabilistic
discovery,
method,
yes.
right?
Yeah.
So from that perspective, we had many discoveries which then in the end turned out not to be discoveries because they were just fluctuations.
But in the history of particle physics, I think the neutrino was not expected at all. Or the muon was not expected.
Well, if we go back to the very beginnings foundations, yes, of course, there were many particles
CERN,
which you didn't
many
discover.
particles were not expected.
All these helped then to build up the standard model as we know it
Exactly.
today.
Yeah.
That's certainly true.
But
I
with
was
these
more
big
referring to the
machines,
last years at
typically
LHC.
we probed theory so deep that we dig out the particles that were expected, like the W and Z bosons found at CERN were also expected.
Then depends also a little bit on the historical moments.
Right.
Now, I mean, the standard model is there since decades now. We have used the last decades to test it, and it works so well. And obviously, in the meantime, since there were some hints, like the fact that our universe is done by matter, but obviously we have a matter, antimatter at the beginning, and we know it annihilates. So there's something that we can't completely explain, or we have the dark matter that is something, again, that cannot really stand inside the standard model. The theory community in these years are producing a lot of possible
Scenarios.
extension,
Yes.
new scenarios. So in some sense, it's very probable that now, even if we will find something else, this will be predicted somewhere. So it's difficult to say you are only discovering things that you are expecting. We are expecting potentially a lot of things, and we don't know if and what of these will be the good ones. So
Yeah. Question for Atlas and CMS. By Kylie McNeil. Atlas and CMS seem so similar in objectives and methods. In which aspects are they different? I don't know if it's for you or for somebody else. The questions.
You want to start? Shall I start?
Well, I think if you look at the two experiments structurally, they're different. And CMS stands for compact muon solenoid, and the compact is really because it's 14,000 tons of very compact detector, compact onion, and we are able to be compact because we have a very, very strong magnetic field. So let's say the muon solenoid, the S is the solenoid magnet. And so CMS uses the bending power of its solenoid magnet to measure in detail the momentum of all the particles, and it's a single magnet. So in that way, it's different to Atlas. But let's say the philosophy is similar. We have an onion-shaped detector, and every layer has a different purpose, to measure either a different type of particle or to measure a different property of the particles, so either the energy or the momentum or the charge and so on. Yeah.
Maybe you want to complete?
Yeah, I just can concur that this is exactly the case. So while both detectors are made to do basically the same thing, they use very different methods to achieve that, and that goes from the highest to lowest level. So the trigger strategy of CMS and Atlas, they're vastly different. The detection method of tracks are the detectors employed, they're different. They're still, both are very performant, so the performance figures are very similar. But the reason why we have two detectors is if one detector sees something, and I was alluding to this non-discoveries which you claimed there, then it's very useful to have a second experiment to confirm that what you see, they see as well. And then, of course, you have a strong case that you maybe found something.
Yeah, already your statistics is so demanding, and then you have another one with the same demanding statistics.
Exactly. And the fact that they use different technologies is also very important, because it might be systematics right? You might not understand
Right.
the detector. So if you have a second experiment which uses a different technology, then it's very unlikely that the same systematic will hit you. So that's why it's really important to have these two experiments doing the same thing but in a different way.
Yeah.
I mean, just maybe to highlight this fact that we have two experiments, I think that we wouldn't really believe the discovery of the Higgs if it had only been seen in one experiment. And the fact that we saw the same thing at the same mass in the two experiments at the same time,
Yeah.
this really means it's very, very unlikely that this was something that wasn't real. And since then, we've seen, again, the signals in the Run-2 data. So now it's completely clear that this is a real
Yeah.
discovery. But if we only had one experiment, this would be much more murky, I think.
Yeah, but you keep discovering the Higgs every time you run the machine. So there is absolutely no doubt about its existence. So Philip Blesky is asking, what are the top objectives of the LHC for the machine, for the experiments, for the next years? Just a quick overview of the next few years at CERN. Maybe we start with the LHC collider.
So with the LHC collider, so the word we use to describe how much data the accelerator can deliver to the experiments is the luminosity. And last year was a big, 2016 was a big important year because the LHC broke the luminosity record, so they went past their design value for the luminosity, which is 1 × 10⁻34, and they surpassed this by about 50%. And this year and next year, they hope to be able to get to about double this design luminosity. So this would be a big achievement. And I think
Already
this is
2017, 2018?
Yeah, I think by 2018 we hope to be able to get to about 2 × 10⁻34. And one of the ways we do that, as I mentioned earlier, is increasing the number of bunches that we have colliding in the experiments. And so this would be another achievement, I think, to try and push to get the machine full of bunches to the design value of 2,750 or something. So I think these are the two big things to happen in the next 2 years in the LHC.
Yeah.
And then there's going to be a long shutdown. And after the long shutdown, what we hope to do is to push the energy of the collisions up to the design energy of 14 TeV. So at the moment, we're colliding the protons together at 13 TeV centre of mass energy, which is close to the design. But you need more energy to produce more heavy particles. So it could be that there's new particles that are out there which we couldn't see with 13 TeV collisions. But if we can push to the design value of 14 TeV, we could start to be able to produce these particles. So this is something that's very important for the long-term prospects of the LHC, and something that we hope to do in 2021 would be after.
But
this
you're already
long
preparing
shutdown.
for that.
This is a big process. It's very hard to get the magnets up to the currents that are needed in order to operate at 14 TeV, and there's a lot of thinking about how to get there, which will happen in the next years.
And of course, the program of the experiments has to follow this increase in luminosity and prepare for that. I don't know if you want to add something to that also from Alice, from LHCb. Yes.
Yeah, also for LHCb, it's important, and we are also working for our upgrade plan because, as was said in the next long shutdown, we will replace our tracking systems. So there's a lot of work ongoing. So this next year will be very busy and exciting because you have people that are really working on the data we are acquiring and operating the detector that is alive, and then preparing for the upgrade and the following phases. So.
Okay, our social media managers through this iPad are telling me it's time to say goodbye from the CERN Control Center, where the LHC has been colliding protons for the last 24 hours and is continuing. The 2017 physics seasons has started for the LHC experiments. Our series of live events on Facebook to follow the hashtag WhatsApp LHC is concluded today, but we won't stop coming live on Facebook, so keep following us. In the meantime, you can still send your questions, and the physicists around the table, and also all the other physicists, there are 3,000 in Atlas, 3,000 in CMS, 1,000 per experiment, LHCb and Alice. They will be happy to answer your questions, so keep asking your questions. Thanks to everyone involved, to our guests, to the tech team, to the CERN Control Center. They are working here around us, and they are putting up with us for the last 24 hours as well. And we are looking forward now to another year of good physics at the LHC. Bye-bye.
Ciao.